In lesson 8.5, we're going to learn how to apply the standard normal distribution to word problems involving teams or athletes. There are basically 5 steps that you're going to do for these problems. So we'll kind of walk through the 5 steps first, and then we'll apply those in a couple of examples. Step number 1, you want to sketch a labeled curve based on the athlete's mean and standard deviation, and these will be given to you in the problem. Step number 2, you want to shade the portion of the curve that applies to the problem. So sometimes it will say less than or exceeds or between two numbers, and you want to be sure that you shade the appropriate portion. Number 3, you're going to calculate the z-score for the athlete's performance. So not only will you be given the mean and the standard deviation, you'll be giving a particular performance that you're interested in finding the probability of happening. Number 4, you want to shade the corresponding area on the standard normal distribution. And number 5, then you'll go to table A to find the area under the standard normal curve corresponding to your calculated z-score. So those are basically the steps that you're going to do. And in most of these problems, I'm going to show both curves. I'm going to show the unstandardized and the standardized curved just to help make the connection between the two. But when you do these problems, you may get to the point where you maybe only need to draw one curve. But I think at least when you first start doing these problems, it's helpful to look at both kind of side by side. So we're going to go back again to Peyton Manning. And we know that in this 10-year period during his career, he averaged 259 passing yards per game with a standard deviation of 74 yards. The curve that's printed in your notes has this horizontal scale already labeled with this mean and standard deviation. What we want to know is in what percent of Peyton Manning's games would you expect him to pass for less than 296 yards? Now, earlier in the chapter, we were able to answer questions like this, but we were restricted to using numbers like 333 or 407 or 481. It had to be one of these whole number standard deviations that were given on the horizontal scale. Now we're looking at 296, and 296 is somewhere in between here. So it's not one of those whole number standard deviations where we can apply the empirical rule. So this is why we need to do z-scores for problems like this. So first I'm going to draw a vertical line in about where I think 296 yards is. Step number 2 is to shade. So less than 296 would be everything to the left of that. So that's step number 2. The next thing we want to do is we want to calculate a z-score for this performance. So we know that it's somewhere between the mean and one standard deviation above the mean, but we need to know exactly where that value falls. So we'll calculate our z-score. So I'm going to do his performance, 296, minus the mean, 259, divided by the standard deviation that year. And that gives me a z-score of 0.5. So we're exactly halfway between 259 and 233. Now, on my standard normal curve, I know now that I can draw a vertical line where I have a z-score of 0.5. And my line is not exactly halfway in between. So I apologize for that, but I labeled it there so we know that we're drawing our line at 0.5. And we want to shade to the left. We're shading the same portion of the curve that we did on the unstandardized version. Now, this is where we go to table A. We're going to look up our z-score of 0.5. And because it's positive, we're going to use the positive side of our table, the front side. And the z-score is 0.5, and there's not a second digit there, so we'll use the 0.00 column. And notice those intersect at 0.6915. Does that make sense? Did we shade more than half the curve? We did shade a little bit more than half. And so because our area there is 0.6915, we can say that we would expect in about 69.15% of his games, we would expect him to pass for less than 296 yards. Now, the last few steps of that problem where we draw the line on this standard normal curve, look it up on table A, that's exactly what we did in lesson 8.4. The only thing that's different is that we have to get the mean and the standard deviation and calculate the z-score before we can get to that step. And that's really the only thing that makes this lesson different from the previous one. All right, and example number 2 says during the qualifying round in the 2010 Indianapolis 500, Danica Patrick had an average lap speed of 224 miles per hour with a standard deviation of 0.7 miles per hour. Assume that the distribution of her lap speeds was approximately normal. In what proportion of her laps would you expect her speed to be between 224 and 225 miles per hour? Again, you've got both curves labeled there for you in your notes. So in the curve on the left, 224 would be right about there. 225. Oh, so I'm going to draw a vertical line on the second curve in approximately the same space. 225 would be right about there, just right above 224.9. So I'll draw a line on my standard normal curve in that same spot. And we want to know in what proportion of her laps would you expect her speed to be between those values. So we're going to shade in between and shade in between over here. Now here we're going to have to calculate two different z-scores. We need one z-score for 225 miles per hour, one z-score for 224 miles per hour. And I'm guessing that this one here is going to be 1 point something, just a little bit above 1. And this one is going to be a negative z-score, right? We can tell that from where it's drawn on the curve. So let's do those two calculations. For the lower performance, the 224, I subtract the mean of 224.2 divided by the standard deviation, and that gives me the negative z-score that I expected. For the lap speed of 225 miles per hour, I subtract the same mean, same standard deviation. That gives me a positive z-score of 1.14. And be careful with rounding here. So I have a negative z-score and a positive z-score. Those look right based on where we drew our lines in our graph. And now we're going to look those up on table A. And because we're looking for the area between two z-scores, we're going to look both of them up separately and then subtract to find the area in between. So when I looked up 1.14 on table A, I got 0.8729. When I flip the table over and look up negative 0.29 as a z-score, that gives me an area of 0.3859. The difference of those then is 0.4870. So we would expect that in about 48.7% of her laps, she would be between 224 and 225 miles per hour. All right, in our last example, we're going to look at a Wimbledon tennis tournament. And we know the distribution of speeds of Rafael Nadal's first serve was approximately normal with a mean of 115 and a standard deviation of 6 miles per hour. We would like to know what proportion of his first serves exceeded 123 miles per hour. Now in this one, I've left the curve on the left blank for you so you can practice labeling it again. So we're going to do that first. So the mean is 115. Remember, that goes right in the middle. And the standard deviation is 6 miles per hour. So we're going to count by sixes on the vertical scale. And I just went down 2 standard deviations in each direction. That's enough for me to solve this problem. So that will give me a good enough idea of what my picture is going to look like. So we've got our curve labeled and the standard normal curve is there as well. Now we'll draw our line at 123, which is the performance that we're interested in. When it says exceeds means more than. So in this one, we're going to shade to the right. And now I can tell from my picture, this would be 1 standard deviation above the mean, and this would be 2. So we're somewhere between 1 and 2, but we need to know exactly where. So this is where the z-score calculation comes in. So we'll calculate his performance, 123 minus the mean of 115 divided by the standard deviation of 6 miles per hour. And that gives us a z-score of 1.33. And just another reminder, we always round z-scores to 2 places, and you want to be sure that you follow the rules of rounding. So it's not 1.3, it's not 1.34, 1.33 if we round that correctly. Now on the right, 1.33 standard deviations above the mean would be right about there. We'll shade the area to the right of that, and then we're going to look up that value on table A. And again, remember, because we're shading to the right, when we look up 1.33 on table A, it's going to tell us the area to the left. That's going to be a number that is greater than 50%. We want that little small area to the right. So we have to subtract that from 1. So 1 minus 0.9082 gives us 0.0918 or 9.18% of his serves we would expect to be faster than 123 miles per hour. Please do homework 8.5 in your assignment packet.